There are a couple of more things that need to be proven. I've said that I've claimed but not proven that doubling x always changes y by the same factor for any given power function. Haven't proven that yet, but I've then shown you how to construct a factor 1.5 function, doublings of x, y increasing by factor 1.5 with each time. And I've claimed that the factor for the power function y equals x to the p is 2 to the p. Now, if we can prove this, we simply use the properties of logs and we can prove this. So this is kind of a corollary to this theorem, if you like. It's like a theorem, a corollary. That p is log base 2 of the factor, and that follows just instantly if we can understand the laws of logarithms. Now, there are a couple of other things that are important to prove, and I'll say this. If your factor is bigger than 1, then as x approaches 0, this means x gets closer and closer and closer to 0 with no restriction on how close. So, for example, if you keep moving halfway toward 0 along the x-axis, halfway toward the origin, there's no limit to how close you're going to get. Okay, in any case, if as x approaches 0, then, if the factor is greater than 1, then the y value must also approach 0. Now, in mathematical language, there's a more compact way to say this, but I'm going to leave it as this. Okay. Now, also, if the factor is less than 1, then as x approaches 0, y must approach, and I left a letter out there, so that's there's a little tiny O in there, y must approach infinity. Now, the idea of limits and limiting values and infinite limits and so forth is often dealt with at the end of a pre-calculus course. So if you haven't had a calculus course, this whole idea of limiting values and so forth might be a little mysterious, but this simply means what we saw earlier, that if I keep cutting x in half, then I got to keep cutting y for this factor by factor 2/3, or I got to keep taking 2/3 of the y value. And it's pretty clear that if you keep taking half of a number, it's going to approach 0. And if you keep taking 2/3 of the number successively, it's going to approach 0. And that's really what we're talking about here. Looks like I left the O out of approach here. I'm approaching 0. Okay. We approach 0. A little better O there. Okay. And what do we mean by factor less than 1, that y must approach infinity? Simply means that as you keep cutting x in half, y keeps getting bigger. And I have to stop and think about that for a minute. Never mind. I don't have to stop and think about that. I don't know. Okay. So yeah, it's what I said. I had to prove that to myself, because for a minute there it didn't seem right. But yes, I know it's true. So as x keeps getting cut in half, y keeps getting bigger if your factor is less than 1. And you can start constructing a graph by that rule and see what happens. You might think of starting with some x value and cutting it in half, cutting it in half, cutting it in half. If the factor is less than 1, for example, if the factor was 1/2, then what would happen? Every time x was cut in half, the factor the factor tells you how much y changes if x is doubled. Okay, if the factor is 1/2, then cutting x in half would end up doubling the value of y, and so forth. Now, I don't want to talk too much about that because I want you to actually think about what these things mean, and we're going to do this in much more detail anyway. So, just giving you a little picture of where we go with this model. The other thing we want to talk about is, what's the scale of this graph? Well, as it turns out, we could put any scale we want on x, we could put any scale we want on y, as long as we have an arithmetic scale, a scale where the x values change always by the same amount when the distance on the x-axis is always the same amount. In other words, a consistent scale, what you're used to constructing, okay? And same with the y. This can't be 1, 2, 3, 4, 5. If this is 1, then this is 2, and then since x is doubling, this is 4, and this is 8, and this is 16, and so forth. So how can we scale this graph? Well, it turns out that we can scale it, as I said, any way we want. We can pick any point on this graph and give it any x and any y coordinate we like, and we're going to get a power function that's equal to, in the case of a factor 1.5, the power is going to be equal to the log of 1.5 divided by the log of 2. We get a numerical approximation of that factor, but that is the factor. So, what we really would do initially, let me grab another piece of chalk here, different color, is we can pick a point on this graph, any point, and call it 1, 1. Okay, because we know that if x is 1, then 1 to any power is 1. So we know that the point 1, 1 lies on the graph of any power function x to the p. So if we pick any point and call it 1, 1, and let's just assume we want a nice equal scale for x and y. So we come over this far, that's going to be our x value. We're going to call that 1. We come up here and project over here, and here's our y value, 1. Now, if we just keep moving in increments of this distance, we're going to get x equals 2, 3, 4, and so forth. We're going to get y equals 2, 3, 4, and so forth. So, by declaring this point here to be the point 1, 1, we now have a graph of y equals x to the p. So this is the graph of y equals x to the p, where p is log of 1.5, things are getting a little crowded here, divided by the log of 2. Those details aren't completely important right now. Again, we work through this in more detail as we move on, but if you can understand it now, it's good. If you don't understand it, at least your mind is starting to churn over it. You're starting to think within this context. Okay, so this is the graph if we declare this point to be 1, 1. So if we want to know what the value of this function would be for x equals 2, we just move over here to 2, and we come up to the graph and we project over. So here's 2, and this point would then be that was an extraneous mark, 2 to the p. If we want 3 to the p, we come over here, we get that. Of course, using the graph to determine the values of a power function is not very accurate. And we have to use better tools to get more accurate values, but we see, at least graphically and geometrically, what's going on here. Okay, well, what if we want to find, what if we want a function where x is raised to the power of p, but y doesn't equal 1 when x equals 1? How are we going to deal with that?